This is a video from the Exam 1 review in my linear algebra class. Let's take a look at problem 12. Let A be an m by n matrix. Let C and D be scalars. We want to show that C minus D times A is equal to CA minus DA. Step 1, or first step, we want to show C minus D times A and CA minus DA have the same dimension. A is an m by n matrix. That's given. Multiplying a matrix by a scalar does not change the dimension of the matrix. And so what that tells me is that C minus D times A, CA, and DA are all m by n matrices. Additionally, the difference between two m by n matrices is also an m by n matrix. And so therefore, C minus D times A and CA minus DA are m by n, and they have the same dimension. So that's the first step of this proof. The second step of this proof, we need to do the following. For each I and j, we want to show that the entry in the ith row, jth column of C minus D times A is the same as the entry in the ith row, jth column of CA minus DA. So how does this work? So what I'm going to do is I'm going to start on the left-hand side. So I'm going to look at the entry in the ith row, jth column of C minus D times A. Well, by scalar multiplication, essentially I can take this C minus D out in front. So this is equal to C minus D times the entry in the ith row, jth column of A. Now, real numbers have the distributive property. And so essentially I can write this as C times the entry in the ith row, jth column of A minus D times the entry in the ith row, jth column of A. But by scalar multiplication, we can write this as the entry in the ith row, jth column of CA minus the entry in the ith row, jth column of DA. Okay? So scalar multiplication gets me from the second line to the third line. And then scalar multiplication again gets me from this first step to the second step up here. The distributive property gets me from the first line to the second line, because C, D, and the entry in the ith row, jth column of A, those are all real numbers. Okay? But the way we define matrix subtraction, we can write this as the entry in the ith row, jth column of CA minus DA. And if you notice, that implies that the entry in the ith row, jth column of C minus D times A here is equal to the entry in the ith row, jth column of CA minus DA. And so that implies C minus D times A is equal to CA minus DA. And one thing I want you guys to understand, when we talk about I and J, contextually, I is less than or equal to M and greater than or equal to 1, right? Because I is dealing with the rows. And then J is dealing with the columns. So J is between 1 and N. And I hope that's okay. So in the first half of this proof, we talked about the dimension, making sure they have the same dimension. And in the second half of the proof, we wanted to make sure that no matter what I and j we chose, that the corresponding entries will match. And in fact, they do. Now, here's a good exercise. For this. Now, one you can do is this. Show that A times BA is the same as AB times A. That's a good one. Okay. Another one you can do, or we can try again, is we want to show A plus B plus C is the same as A plus B plus C. In either one of these two type of problems, remember A, B, and C are matrices. And in this one, this first one, little a and little b are scalars. What you do, again, is you're going to show that the matrices have the same dimension. And in the second half of the proof, you want to show that the entry in the ith row, jth column of the left matrix is the same as the entry in the ith row, jth column of the right matrix. So you want to make sure that the corresponding entries match, because if the corresponding entries match, then the matrices are equal. Okay, that's going to conclude this video for the Exam 1 review, and we looked at problem 12. Thank you.